Today is Monday, September 29th, 2025. This is First Alert Weather Plus. Meteorologist Nicholas Snyder here. We have a very special edition of First Alert Weather Plus. We're talking all about tornadoes today. I'm interviewing a very big name in the tornado research field, Dr. Jana Houser, currently a professor at Ohio State University. And when I was at Ohio University back in 2017 through 2021, my undergrad advisor, yes, she did used to work at Ohio University, talking all about how topography can impact tornadoes, how we can see tornadoes form, new theories on tornado formation, and what exactly we can view tornadoes with as far as using mobile radar and things like that. So without further ado, here's my interview with Dr. Jana Houser from Ohio University and now Ohio State University. Let's start with the bottom-up tornado genesis theory, kind of how you came up with it, how you really just went about going about figuring this out and things of that nature, and when did this come about?
The idea of the bottom-up or non-descending tornado genesis paradigm originated when I was a graduate student at the University of Oklahoma. And so it had its foundational work in my PhD dissertation. So I had looked at one specific tornado and found that for that tornado, there was definitely no evidence of top-down. And instead, it was kind of a simultaneous conversion of larger scale rotation into basically one cylinder that was rotating quite quickly. So that was kind of laying the foundation. And I also had a colleague of mine who was kind of simultaneously investigating a similar problem using slightly different data sets. And he also came to the conclusion that this top-down idea was actually a function of the fact that we had radar data that were inappropriately sampling the storm, so sampling at too long time increments in between. So it created this sort of false sense that you had this process that was temporally consistent starting from the top and then moving to the bottom. And in reality, what he found was that you had small scale, transient, short-lived areas of rotation higher up in the storm, and these kind of came and went. And when we resolved the storm with higher time frames, we could clearly see that the short-lived ones were not connected to what was happening at the surface. But when you broke down and kind of like falsely created a sense of longer time frames, it actually made it look like it was coming from the top and building downward. So this kind of planted the original seeds of this idea that maybe our conceived notion of how tornadoes form in supercells might not be correct. And so there was another pivotal study that came out several years later that investigated the El Reno tornado of 2013. And a colleague of mine put together a really fantastic visual database from storm chasers into an environment where everything was temporally accurate down to hundredths of the second. So when you time stamped, you could see the timestamp going, and you would see a funnel cloud, and you would see rotation on the ground. And when I compared those visuals to what we were looking at in the radar data that I had been there to collect, I noticed specifically that there was a visual of a funnel cloud, and it was before the time that we attributed to tornado formation. So when I went back through the radar data and dug around a little bit, I realized that the reason for that was because we, in our analysis, threw out the data that was at the very lowest elevation angle, basically parallel to the ground, because it was a little bit contaminated with trees and objects that reduced the velocities. But you could still see the tornado rotation, and it turned out that there was a signature for a tornado in that very lowest data. So this is data that we're looking maybe 30 to 50 meters above the ground. A minute and a half prior to the data at the next elevation angle up, which was what we were forming our scientific consensus ideas on. And so that was a really clear smoking gun that at least in that tornado, there was something definitely starting at the ground and then building its way upward. And so this idea was like, okay, we're having a handful of cases here now, and we need to, if you have a theory, you need to make sure that everything conforms to that theory. So we needed to find additional cases. And so over the next several years, I spent time digging through the radar data that I had and really applying this idea to an additional 8 and now we're up to 12 tornado cases, all of which conform to the non-descending paradigm.
And for those who may not be familiar with how you can detect tornadoes on radar, kind of what do you look for to kind of show you how you saw that tornado kind of form on the radar picture?
Radars are only capable of looking at motion towards or away from the instrument. So you can't, if I have a radar beam that's going this way, I can't detect something that's going that way. I can only see something going that way or that way. So what that translates to for a strongly rotating vortex like a tornado is that you end up seeing an area moving towards the radar on one side right next to an area moving away from the radar on the other side. And so you can kind of fill in the gaps and implies rotation. So in our radar data, there are a variety of different scales of rotation that we can see in the storms that end up producing tornadoes. So you have a larger scale rotation that we refer to as the mesocyclone, which is the parent thunderstorm that's rotating. But then you have the tornado scale rotation that's smaller and inside the larger scale rotation often. So when you see those two signatures kind of back to back, the inbound velocities right next to the outbound velocities, we know that there's strong rotation there. And then that can be confirmed by additional parameters that tell us when we have debris in the air. So if we see that rotation and the debris, we are 100% confident that there is a tornado ongoing.
And you mentioned too some of the other radar images that you looked at didn't have good enough time resolution. It was too slow. But in this specific case, you had a more rapidly scanning radar. Talk about some of that technology that you've been using and some of the new stuff that could be coming out sometime in the future with these rapid scan radars that could help us.
Yeah, so one of the things that we know about convective, specifically convective hazards, such as tornadoes and severe thunderstorms and the wind fields that are inside these storms, is that they change and evolve very quickly. A traditional radar that you might see, like a radar image from the Weather Service or on your nightly news, those collect data over time scales that are on the order of 4 or 5 minutes typically. So you can imagine that if you have a tornado, for example, that I just described, it can form on time frames of like 1 to 2 minutes and sometimes even less. We've seen basically nothing to tornado in time frames of 45 seconds or so. Um, the traditional radars are going to miss that process entirely. So you're going to go from absolutely nothing to all of a sudden having a tornado. Or in situations where you have weak tornadoes, you might miss the tornado entirely because it's only lasting 1 or 2 minutes. Some of the really cool new technology that exists out there are these rapid scanning radars, which are the primary tool that I use to observe and study tornadoes. The way those instruments work can vary from instrument to instrument. There are some that the antenna actually spins very quickly. And by doing so, it can collect data in a very rapid sense. That requires very specific instrumentation techniques, and not all radars are capable of spinning that quickly and achieving a similar result. Most of the time, that's actually just going to smear everything out and make your values for your velocities and for the other parameters that the radar is looking at to actually be inaccurate. So that takes special technology to do that. There's another technology that's referred to as phased array technology, which is where you have basically a whole lot of tiny little antennas that are arrayed in a square panel. And each individual antenna has a time sync control that tells it when to transmit energy. And you can essentially create the radar transmit energy in a way that allows you to very quickly change directions, like in like thousandths to 10,000ths of seconds. You can get a very fast changing radar picture. So we can put together, using one of these phased array instruments, simultaneous pictures that go both in the horizontal and in the vertical. And you can collect data. If you don't move the antenna and you look at sort of a small portion of the sky, you can get updates every couple of seconds. So obviously that's really going to be important for studying these phenomena that are so quickly evolving. You can also physically rotate that phased array antenna so that you're looking at slightly different parts of the storm, and so you can kind of lump everything together to get a rapid sense of what's happening internally to the storm.
Gotcha. And I know we have some mobile radars too. A lot of the researchers have been using, including now at Ohio State, right? You guys have now a mobile radar that you're using. So can you touch on that and how that can really kind of help us figure out tornado genesis going down in the long term?
Yeah, I was awarded an internal grant through The Ohio State University that is funding the development of a brand new radar that is basically the total top of the line for what our technology can provide right now. So it's one of these phased array antennas that can get really high temporal resolution accuracy, and it's coupled with another feature that allows us to see the shape of precipitation and to make those detections between what are we looking at. Is it rain? Is it hail? Is it debris? And so using this information together allows us to go out to storms and kind of almost use X-ray vision to see what's happening inside the storm. We can look at the distributions of hail. We can look at the distributions of large raindrops versus small raindrops. We can see how that's changing very quickly in time. We can also get information about the wind field, and we can see where there are boundaries within the storm, where there's small areas of rotation within the storm. Ultimately, if you get kind of close enough, you can see very low levels, and we might be able to see things like predecessory small scale areas of rotation. So basically, little whirls before the actual tornado forms. There's an increasing body of evidence that has accumulated from numerical simulations of tornadoes that suggest these sort of chaotic small scale areas of rotation present at the ground in the first place kind of congeal and can get sucked into the storm from below, and that ends up being the trigger for your tornado formation process. The challenge is that it's difficult to observe in nature because they're so kind of small scale and quick to kind of come and go. So one of the things that I hope to do with this new instrument is to take it into the field and to investigate whether or not we can actually see these small areas of rotation to really help us understand the processes that are behind the formation of tornadoes. And ultimately, what that does for science is it allows us to better understand what conditions we're going to need for tornadoes to form in the first place. And then we can back out and essentially use that in a forecasting sense.
Shifting gears a little bit now to some of the other research you're doing on topography, there's a big myth, and you told me this when you were teaching me in class, that everyone thinks that because you're in a hilly zone or you're near mountains that tornadoes can't happen, but that's obviously not true, and especially in our area where we are right here, where there's a lot of hills, there's a lot of mountains, a lot of people still of the belief of that. So talk about what you found in terms of how topography is impacting the strength and maybe the track of a tornado, and why this myth is just not necessarily the truest thing.
Terrain really complicates the organization of the low level winds, which are ultimately what's feeding the tornado in the first place. So when you have an ongoing tornado that's approaching a hill or a valley or a series of hills and valleys, the presence of those hills and valleys will affect the tornado and the air that's being ingested into the tornado. Now, what the end result of that ultimately ends up being is complex and has to do with how the tornado is approaching the hill. Is it coming straight onto the hill? Is it coming up the side of the hill, or like kind of parallel to the hill, so that like one half of the tornado is on the mountain or the hill and the other half isn't? It also is important to note how tall the hill or valley is in the first place, because if you have an obstacle that's too tall, oftentimes it does end up causing the tornado to dissipate. However, I've used very high resolution modeling simulations where we're actually putting in like real life terrain from the earth, and we're putting it into this modeling framework and having a tornado moving over that. And what we end up finding is in scenarios where you have moderate terrain, so we're talking kind of just like, hills that are maybe like 100 to 200 feet, in those simulations, almost ubiquitously, you have a tornado achieve a higher intensity, so faster winds, than you do if the hill wasn't there in the first place. Now, the tricky part is that it's not consistent where that wind maximum actually takes place. And this is where the attention to details is very complicated, and like real life kind of breaks down because you can't generalize the real terrain with like, just a simple hill or simple valley. But for those intermediate terrains, oftentimes what can happen is you can actually accelerate the winds going into the tornado through the channels between two hills, for example, or between a valley. And that acceleration actually contributes to enhanced rotation that the tornado can access and then ingest and become stronger. So it is a myth that your house or your town is going to be safe from tornadoes because they have this complex terrain nearby. And this is even the case where you have higher terrain in places like in the Appalachians and even in the Rocky Mountains. There are certain configurations where the terrain actually enhances the wind pattern in a way that causes a tornado to form, when if the mountain or the valley wasn't there in the first place, you wouldn't have actually had the conditions favorable for the tornado. So it's very localized and it's very difficult to generalize because the weather has so many different configurations and different ways of approaching those various different barriers.
And you mentioned too, I heard you talk on it really depends on kind of the angle that the tornado kind of hits it at. Could you elaborate on that a little bit more?
Yeah, so if the tornado is going to go is if you have a mountain this way and the tornado is approaching this way, if the mountain is high enough, the tornado will tend to dissipate as it goes up the hill. Now, sometimes if the parent rotation is still present, it will intensify going or reform going down the other side of the hill. But if you have a hill that's oriented this way and the tornado is moving parallel to that, it's doing that channeling effect, and it's actually going to potentially enhance the intensity of the tornado.
Shifting gears a little bit one more time, I know over the last few years you've been developing kind of a database of severe weather in Ohio, for instance. Could you talk about what you found as far as storm reports, climatology in Ohio, and where the most at-risk places could be?
Yeah, so we have put together all of the storm reports that are official from the Storm Prediction Center and the National Center for Environmental Information. And we've tabulated this all into a database that is county based, so county specific for the state of Ohio. And we've included information such as economic losses, fatalities, as well as the intensity of the tornado, the number of tornadoes that we have seen in the database from the inception of storm reports back in the 1950s, the time of day that the tornadoes occur, etc. And so what we tend to see is a little bit of clustering of tornado reports around areas that have higher populations. And this is not saying that tornadoes are necessarily more prone to hit towns or cities, but instead we're more prone to seeing them when they happen in those areas. So the counties in and around Columbus, in and around Cincinnati especially, and then there's a couple little other hot spots across the state that do end up having more tornado potential. But then there are also counties in the southeastern part of the state where that is the opposite, and where there are fewer tornadoes than the surrounding areas. And one of the things I'm looking at with a student right now is trying to investigate what's happening there. Is that a function of the environment? So is like the environment actually modified, perhaps by the presence of the terrain that exists in the southeastern part of the state? If we get a signal that suggests like the environment's not being modified, then is this something where the terrain is actually on a localized scale, perhaps disrupting the flow? Or the third possibility is that we're just not observing them. So that, we have fewer people out there in the southeastern portion of the state, and there are significant barriers to visibility, including hills and trees and things like that. And it's possible that we're just underreporting the tornadoes in those locations as well. So that's a work in progress currently, and hopefully in another year or so we have some more conclusive answers for you.
And if people wanted to view kind of the database, kind of the raw storm reports that you had, I know you have a website for that. Is there a way that people can find that?
Absolutely. So if you do a Google search for Ohio tornado dashboard, that should come up with a website that is through Polar and Climate Center at OSU, and you click on that, and that is sort of the home base for all of these various different pieces of information. And I would like to add also that it's not just for tornadoes. We have information in there about hail, about thunderstorm winds, and even flash flood and flooding hazards. Our tornado, hail, and thunderstorm wind database is updated through the end of 2024. And the flood climatology is updated through 2022. So we're a little bit behind on the flooding, but we just recently, actually over the summer, updated the database to include everything up through the end of 2024.
Dr. Jana Houser at Ohio State, thank you for taking the time today to talk to everybody. I'm sure this is going to be really interesting for a lot of people. Great stuff there from Dr. Jana Houser of Ohio State University, former professor at Ohio University. During my time there from 2017 to 2021 at Ohio University, she was my undergrad advisor, and I definitely learned a lot from her, so I was glad to have her on First Alert Weather Plus this week. Let's shift gears now to the weather. We've seen a lot more rain over the last week, and meteorologist Hannah Hayes is explaining why this has an effect on our overnight low temperatures.
The overnight lows over the next few nights will feel more muggy, humid, and mild compared to the nice overnight lows we had when there was little to no humidity in the air. When there are clear nights, cooler temperatures will always occur because of something called radiational cooling. Radiational cooling is where the surface of the Earth radiates heat that it absorbs during the day into the atmosphere without any absorption by the clouds. When there is cloud cover, like this example, the warm air has nowhere to go, resulting in the warmer nights. But when there aren't any clouds on a clear night, the temperature will be cooler because radiational cooling is allowed to occur since there's no cloud cover. This week we will have more humid days and cloudier nights, and that's going to result in some higher overnight lows. Now, as you can see, over the next couple of nights for the week, they are expected to be into the 60s for the first several nights. We will have cloudier and more humid days expected, so naturally at night, radiational cooling will not be able to occur because the heat absorbed during the day will have nowhere to go since we have more cloud cover. Now you notice towards the end of the week, the overnight lows are expected to drop back down into the 50s. This is due to the fact that there will be less cloud cover on those days associated with those lower rain chances.
Great stuff, Hannah. Thank you for that. That's why it has been a little bit warmer in the mornings compared to when we were in that drought, or at least the drier weather. We did see those overnight lows a lot cooler compared to where we're at now. This is First Alert Weather Plus. We give you the first alert on everything you need to know, from floods to tornadoes, anything you want to know in the weather world. We've got you covered on that. You can follow each of us on Facebook for daily updates. I'm meteorologist Nicholas Snyder. Dylan is Dylan Goday Weather. Tony is Tony Cavalier. And Hannah is meteorologist Hannah Hayes. First Alert Weather Plus airs every Monday, 6:30, 6:45 p.m., and we give you, again, the latest on what you need to know. You can find us on YouTube, WSAZ First Alert Weather Plus. Be sure to like and subscribe. We do some exclusive content on the YouTube channel as well, including the Wednesday Weather Lab, giving you some cool experiment ideas to do with your kids. In the meantime, I'm meteorologist Nicholas Snyder. Make it a great Monday.